Welcome to SumLab. We have seen how electrons are arranged in an atom and how this arrangement is reflected in the shape of the periodic table. In this video, I want to demonstrate how the elements are sorted into two broad categories, metal and non-metal. Note that we're talking about elements. There are metal and non-metal mixtures and metal and non-metal compounds as well. I'm not talking about those. Chemistry is full of such subtleties. There is a simple idea behind metal elements, which, if you get it, will really help you to understand a lot of what goes on in chemistry. On the periodic table, if we draw a straight line here, we find the metal elements to the lower left and the non-metal elements to the top right. Now, we all think we understand what a metal is: strong, hard, malleable, shiny, conducting electricity, and that would be right. But these are all physical properties. In classifying elements, we're interested in chemical properties, and one property in particular. Metallic elements react by losing electrons. Non-metal elements don't. That's it. That's the definition. An element is a metal if it loses electrons. So let's have a think about why. Here is a piece of sodium. A chemist would regard this as the quintessential metal, and it is very useful in the lab for its chemical properties. Its atoms have a completely full first shell, a completely full second shell, and one lonely electron sitting by itself in the third shell. This is the party planning equivalent of sitting this guy by himself at a big table. He is not going to stick around. He's going to leave and find another party. Maybe this one. There's an empty space. Metals lose electrons, non-metals gain electrons. The end result is that all the tables are properly filled. Chemists often speak about gaining or losing electrons to achieve a complete outer shell, often referred to as the octet rule, since the S and P subshells together hold 8 electrons. This is a slight simplification when it comes to larger atoms. It is more accurate to say that metal elements lose electrons to attain a stable electron configuration that includes full shells and subshells. Here is a piece of zinc metal. I drop it into a solution that conducts electricity and connect it to the positive electrode of a power supply. And because electricity flows in a loop, I complete the circuit with an inert electrode. Now, there's a lot going on here, but I want to focus on one thing. Electrons are negatively charged. They are attracted to the positive terminal of the power supply. The lonely outer shell electrons are going to leave the zinc and travel along the wires to find somewhere else to party. After a short time, the zinc has completely corroded away. A reaction has taken place and the zinc atoms have each lost 2 electrons. The logical question then arises, where did the zinc atoms go? The answer is that they are not called atoms anymore. They are still called zinc, but now they are zinc ions and not atoms. So what's the difference? What is an ion? Very simply, a metal atom becomes an ion when it loses 1 or more electrons. And non-metal atoms become ions when they gain electrons. This is not some subtlety in chemistry terminology. This is a critical concept. The reason for the name change is that ions have completely different properties from atoms. Ions have an electrical charge. Metal ions or cations have a positive charge, and non-metal ions or anions have a negative charge. And it is this charge that causes a big difference in how they behave. Because of their charge, they experience a physical force when they are placed in an electric field. Therefore, they can be moved around by an applied voltage. A second difference is that ions dissolve quite nicely in water. This happened in our experiment and is why the zinc strip corroded away. A third difference is that positive and negative ions attract each other because of their opposite charge. They have the ability to stack together in an ordered arrangement to form a solid material. This is the white stuff visible in our experiment. There are other differences between atoms and ions, different size, different interactions with other chemical species. The thing to note is that atoms and ions are completely different things, even though they have superficially similar names. If someone tells you that you need more iron in your diet, it is no good sinking your teeth into a crowbar. You need some ions. And there's another terminology headache right there. What happens if we take a bunch of these positive ions and try to put the electrons back? In this setup, I have zinc ions in a solution. I have a copper electrode attached to the negative terminal of a power supply, and again, an inert electrode to complete the circuit. Flick the switch, and the positive zinc ions are going to be attracted to the negative electrode. They experience a physical force and actually move. When they get there, they find an excess of electrons. They're able to recombine with electrons, and we end up with zinc metal again. All metals behave like this, although admittedly only a small fraction can do this in a watery environment. Well, are there other chemical properties that can characterize metals and nonmetals? Of course. Metals tend to react with acids, and nonmetals tend to react with bases. There are exceptions, there are always exceptions, but as a general rule this holds. In this experiment, I used some acids that are common in the lab: acetic acid, hydrochloric acid, and nitric acid. To these I add magnesium, iron, and copper. Magnesium in acetic acid bubbles vigorously, producing hydrogen gas. Iron also produces hydrogen and begins to discolor the solution as it dissolves. Copper produces a lovely blue in the acid and releases a toxic brown gas. The point is that they all react, in this case quite visibly. What happens if we try the same thing with a powerful base? The answer? Not much. As a rule, metals do not react with bases, at least not in the same way that they react with acids. The reverse happens when you're dealing with nonmetals. This element is bromine. It is a really interesting element and one of two liquids on the periodic table. It is actually stored with concentrated sulfuric acid, which absorbs any water that may be around. And even though the acid is highly concentrated, there is just no reaction with the nonmetal. Now, if I draw some of this up, I can attempt to react it with a solution of sodium hydroxide. You can see, as I shake it, that there is a color change and the bromine droplets in the test tube disappear. I need to add a few pellets of solid sodium hydroxide to complete the reaction. Eventually, all of the bromine has reacted. Iodine is another interesting element and a nonmetal. I add it to some ethanol. In chemistry, it can be a lot easier to work with a liquid than a solid. A bit of stirring, and the iodine is fully dissolved. A couple of drops added to hydrochloric acid, and even with mixing, there is no noticeable reaction. With the base, sodium hydroxide, well, just look, the color completely disappears, which is clear evidence of a reaction. A third nonmetal example, sulfur. It does not dissolve in water, but with a little hot xylene I get a pale yellow solution. For a base, again I will use sodium hydroxide. This time the acid is oxalic acid. Both are solid white powders, but they are very different, as we shall see. A portion of the sulfur xylene solution is added and then it is heated. The oxalic acid actually dissolves in the mixture. It is hot in a single phase. These are ideal reaction conditions. If anything was going to happen, we should see something, but no obvious reaction occurs. Heating up the sodium hydroxide, it doesn't dissolve, but over time we see evidence of a reaction between the nonmetal and the base. The prills of the sodium hydroxide become coated in a solid orange material. This is sodium polysulfide. And within a short time, all of the xylene has clarified as the sulfur has reacted away. These examples confirm a general trend. Metals react with acids, non-metals react with bases. Getting back to the periodic table, metals on the left. They lose electrons, they react with acids, and they form positively charged ions. Non-metals on the right, they gain electrons, they react with bases, and form negatively charged ions. I wonder if metals and non-metals react with each other. We'll call that a yes, but a full investigation will have to wait for another video. That's it for now. See you next time in the lab.